Hello everybody, so I'm Grigori Matein and I'm from the Institute of Nuclear Energy and Nuclear Research, but what I'm going to present has nothing to do with that because my supervisor did topological and all this stuff as a hobby and I did it for fun, and we found some things and it ended up being a PhD, so yeah, I'm gonna show you what we found. These tools, oh, they do work. Awesome. Yeah, so I totally realize the topic is each word is a field on its own. So I'm gonna go one by one, no problem, concept by concept. And I'm assuming no knowledge, by the way, not like the others. So we're gonna start with beauty, and there is a lot of beauty in nature which has been quantified in maths, starting with Fibonacci. So 0 and 1, add them, you get 1. Add the previous one, 1 plus 1 is 2, 2 plus 1 is 3, 5, 8 and 13, and you can keep going. This sequence, that's called the Fibonacci sequence. And it has at least, well, quite a few nice properties. One is that when these numbers are the sides of squares and you connect the angles with circular lines, you basically get this spiral, and this spiral is everywhere in nature. So that's sunflower, that's how it goes. That's aloe, that's the shell of a snail, galaxies, DNA, tornadoes, and I don't even know these two, but yeah, in them as well. One more, Mona Lisa, and actually a lot of paintings. And the reason, well, one very cool thing about Mona Lisa is that it follows this special property called the golden ratio. So this guy, Leonardo Pisano, that's his real name, and he's also known as Fibonacci, so that the bigger to the smaller number, the ratio actually gives you a number which becomes better and better defined. So for our purposes, we're just gonna say it's 1618. Yeah, we won't need all the others. It's a 0 or something. Yeah, doesn't matter. So the thing is, the distance from arms to chin versus the size of the head is the golden ratio, one to the other. Then distance, so the whole head compared to the distance chins to nose is again the golden ratio, and it actually continues, and it can be found on other sides of Mona Lisa. And actually that's why, well, one of the reasons this makes this picture so gold, so unique, and it has been stolen throughout the years and so on. The thing is, we can go big to small, but we can also go small to big, and that's the inverse of the golden ratio, which is exactly one times smaller. Okay, so so far so good with Fibonacci. We're talking currently about numbers, so we keep going with numbers. How about the number 19? And there's something interesting about it. You can decompose it, meaning represent as smaller numbers, like 1 plus 2 plus 16. But what is 1? 1 is 2 to the 0th power, 2 is 2 to the 1st, and 16 is 2 to the 4th. So 1 times of this guy, 1 times of this guy, none of 2 to the 2nd, 2 to the 3rd, 1 times of 2 to the 4th, and none of the rest. And these ones and zeros is actually the bit representation of 19. This is how the computer, every computer, sees the number 19, and actually if we change these bits, we can represent every number in the computer. But not only numbers, the pixels of an image. And when I mean image, I mean this I found on the internet, not just black and white, but colorful full HD images with all the shades of red, green and blue, or at least 68 billion. Well, can be more, but the eye won't get there. So apart from images and videos, we can also do it with sound. So that's one wave, and it can be decomposed in numbers too. Actually, any sound. And so far we have images, we have sounds. Great. What we want is to read the underlying bits. How do we do it? Well, honestly, that's a very nice sketch, but that's pretty much what the computer does. You have a very long tape. I mean, these are billions in the computer. And you read one, then you change it, and according to the state of the system, you do something. So you can change it to 0 to 1, you can go somewhere, and these are the rules. For example, the state is A, we read 1, yeah, so not too good, this one. In a computer, the rules are a bit more serious, obviously, and they're called logic gates. Meaning, for example, the AND gate, we read 1 bit, if it is 1, and the next one is 1, we get a 1 out. So that's what we write. If it is an OR, it's either the one or the other when we get a 1. So basically we read 2, we get a third one. For context, what an AND gate is actually in reality, because I understand we are very abstract here, it's actually a group of transistors combined. That's, by the way, the revolutionary thing of the 1970, 1960, to represent all this, which was known before with transistors. So combining transistors in a clever way can give us these gates, but combining gates in a clever way can give us circuits. And that's the circuit for addition. Simple enough, but the machine can now do it too. And this circuit is actually in all our computers. This gets in the first and the second number. This is the carry from the previous addition. We get the sum out and the carry for the next addition. So gates, working on bits in some useful ways, is what computation is about. Now, why all this? Why do we care about computation whatsoever? Well, the thing is, at least 2 reasons. We have always wanted to predict the future, bad future, and protect ourselves. So, tornadoes, Fibonacci won't be enough here. Bad earthquakes, well, not that there are any good ones. Predict DNA and diseases, predict the economy. If there is a recession, we don't want this. Also, because, why do we care? Well, knowing how the universe works and building new gadgets, new machines is just plain cool. Now, all this, we want to have it. But the major problem is that even clusters of supercomputers are struggling. So we need more powerful computing devices. And you know what has the potential? Quantum. Starting simple again. This is the electron, so that's a nucleus, that's an atom. We all know electrons. They have mass, they have charge, but they have spin too. Meaning, they either rotate clockwise or anti-clockwise, a bit like the Earth. Well, the Earth is going only one direction, but you see, it's like 2 possibilities, like 0 and 1. And exactly it is this property which makes the electron not just a bit, but a quantum version, a qubit. And while a bit can only be 0 or 1, this electron doesn't have to go only this way or that way, it can actually rotate around any axis. And these coordinates, so these lines here, maybe not easily seen, but they look like coordinates, and this arrow looks like a vector. Yes, indeed, there are coordinates and vectors. So, crash course, coordinates and vectors. We can represent a vector by 3, x, y, and z. So, they completely define the system. We put it in this way, we group them together, that's what's called a vector. And apart from distances, we can also use the whole distance of the vector and 2 angles. So if we represent x, y, and z with this, that's how it's called, and these are called spherical coordinates. So, back to our spheres. We were talking about the qubit, and we want to represent this axis of rotation. By the way, that's what we call a state, or in which direction electrons are moving. So, because we can only measure up or down, that's physics, we want to represent it, how much it is of the 0 and how much it is of the 1, and that's the representation. So, yeah, it was a bit late when I wanted to delete this, I had already sent the presentation, but anyway, don't bother about this, bother about that, because we had 3 numbers. In this case, it's always gonna be on the sphere, so we only need 2 of them, not 3, 2. And for example, if this is absolute 0, so theta is 0, only here is gonna point up, so 0 is 1, 0. So completely up. Cosine of 0 is 1 and sine of 0 is 0. Okay, so we have the electron, we have a qubit, we want to change the state of the electron. And how do we do this? With light. Electrons like light, they change from one direction to another, and that's actually a pulse of light. So, because we were talking about vectors, we want to describe this mathematically, we want to predict it, and we do it with matrices. So, very quickly, crash course matrices. And yes, we can describe how matrix multiplication works, so that's basically one pulse, and then you have another pulse, so two matrices, you can mathematically combine them to see what's happening out. But what I want to point at is that if these matrices are full of numbers, we don't really know what is happening. If you increase this 10 times, this kind of increases, but there is this one from here, this increases, but there is one from here, it is not very known. However, if you increase this 10 times, you see all these zeros very nicely. Well, this one and this one only will increase 10 times, so it is predictable. The takeaway point here is we want diagonal matrices. That's what helps us. So, when we combine it all, these are the matrices for the qubit. So this is what acts on our vector, on our state. This is the quantum equivalent of our classical gates and of the light. So if we start from absolutely going up, we apply the X gate, which is this guy, it actually flips it the other way around. And that's what this guy shows. So now, this is just for two more qubits. This guy is 2 qubits, and this is for 3 qubits. So it keeps rising, it keeps going, and that's basically a quick recap. These are the electrons, and these are the pulses. And if you do it in a clever way, you can get circuits just like in the classical version. So that's a quantum addition. Now, what are we missing? Well, we're missing topology. Topology is about, at least in 3D, roughly, how many holes do you have? So basically a cup and a donut is the same thing. And topologists do take it quite seriously. At the same time, a ball is pretty much the same as a cube, which is like a chocolate or a ball if you want. So this is in 3D. In 2D, we have particles or small circles, small things which cross paths. So these two don't cross paths anywhere, and you can basically cancel these, so there are no paths crossing, so it's the same topology. But if two of them cross, you changed it. You changed the state. So keep this in mind. We're gonna go in like one slide on this. So anions is basically the hardest topic, and we only have one slide on it because I won't get into details, but you need very hard, extreme conditions, low temperatures, high energies. So it's in 2D, but let's think about it only as particles lined next to each other. So, where does Fibonacci come in? Now they become Fibonacci anions because 4 particles have how many states? So one thing, what is the 4th Fibonacci number? It's 2. So you see how these are 2? Turns out, if the number of anions increases, the number of states, so the size of these, so if it's 2 of 2, 5 by 5 or something, increases exactly as the Fibonacci sequence. And furthermore, when they cross in space, the state changes according to these matrices, which have the tau, which is 1 over the golden ratio. And yeah, it appears yet again. And that's mind-blowing, just to say, yeah. So we're gonna combine it all. This, ladies and gentlemen, is dots rotated on a surface. And it's also topological quantum computation. Meaning, you rotate these guys in a clever way, you change the topology, and that's what's called a braid. And if you do it in smart enough ways, you're gonna get back to the gates we started from. And basically these operators combined will give you these gates. And these gates are actually what we had just a second ago, which is a quantum computer. Now, that's pretty much what topological quantum computation is with Fibonacci anions. So, what has been done and what did I do? yeah, we have like 3 slides for that. The thing is, everybody for the last 20 years has been trying to get these special gates to achieve whatever quantum computation by brute force. Nobody cared to look for patterns and come up with something actually a bit more meaningful, and at the same time find circuits for more than 1 qubit. So I actually started from the zero, yeah, and starting from these guys here, I managed to get to these, which I call constructors of whichever gate we want. And I can come up with the general one, which will give me these X, Y, Z, or whichever others I have, I would like to have. Not only that, I can keep going and do it for 2 qubits, and in a second I'm going to show 3 qubits. So for example, 6 anyons is 1, 2, 3, 4, 5, 6, so that's number 5. 5 by 5, yep. You see these ones here? So they look a bit ugly, like slightly, but I can transform them into these two and basically inject whichever states I want to whichever qubits. I can do it for 3 qubits too, and yeah, so that's the last slide. The thing is, in 2 words maybe, before us, people struggled to get even 1 qubit gates for 1 qubit systems. We found a way, mostly me, my supervisors did other cool things, but this one was for me. I found a way to come up with whichever 1 qubit gate for however many qubits we have. So basically, now if you give me a quantum circuit, I can decompose it to the rotation of these anyons, which will achieve it in reality. And spoiler alert, these anyons hadn't been found until 3 weeks ago, which is probably a Nobel Prize thing you will see in a year. Yeah, and actually that's it.
Thank you very much. We can continue during the welcome party. It's very interesting, and it seems very intensively developed subject. So during the welcome party, we can continue the discussion. Thank you very much.
Thank you very much.
Thank you to all of the speakers in this session.